Chapter 10, Circles. This presentation on circles will cover the following topics: an introduction to circles and related terms, a detailed look at the tangent to a circle, the number of tangents from a point on a circle. Introduction to circles. A circle is defined as the set of all points in a plane that are at a fixed distance from a central point. Here are some key terms associated with circles. Chord, a line segment whose endpoints are on the circle. Segment, the region inside a circle that is bounded by a chord and its corresponding arc. Sector, the region bounded by two radii and their corresponding arc. Arc, a portion of the circumference of the circle. When considering a line and a circle, there are three possible arrangements. Non-intersecting line, the line does not touch the circle at all. Secant, the line intersects the circle at two distinct points. Tangent, the line touches the circle at exactly one point. Tangent to a circle. A tangent is a line that intersects a circle at precisely one point. A key property to remember is that the tangent at any point on a circle is perpendicular to the radius at that point of contact. Key observations about tangents include: a tangent is a special case of a secant, where the two intersection points coincide. There can be only one tangent at any given point on a circle. Theorem 10.1. Theorem: the tangent at any point of a circle is perpendicular to the radius through the point of contact. Proof: imagine a circle with center O and a tangent line xy that touches the circle at point P. To prove that the radius OP is perpendicular to the tangent xy, consider any other point Q on the line xy. This point Q must lie outside the circle. Otherwise, the line would be a secant, not a tangent. Because Q is outside the circle, the distance OQ is longer than the radius OP. Since this is true for every point on the line xy except for P, the radius OP is the shortest distance from the center O to the line xy. Therefore, OP must be perpendicular to xy. Number of tangents from a point. The number of tangents you can draw to a circle from a single point depends on the point's location. If the point is inside the circle, you can draw no tangents. If the point is on the circle, you can draw exactly one tangent. If the point is outside the circle, you can draw exactly two tangents. Theorem 10.2. Theorem: the lengths of tangents drawn from an external point to a circle are equal. Proof: consider a circle with center O and an external point P, from which two tangents PQ and PR are drawn. We need to prove that the length of PQ is equal to the length of PR. By joining O to P, Q, and R, we form two right-angled triangles, OQP and ORP. We know they are right-angled because a tangent is perpendicular to the radius at the point of contact. In these two triangles, OQ equals OR, because they are both radii of the same circle. OP is common to both triangles. By the right-angle hypotenuse side RHS congruence rule, the two triangles are congruent. Therefore, the corresponding sides PQ and PR must be equal. It is also important to note that the center of the circle, O, lies on the bisector of the angle between the two tangents. Example 1. Concentric circles. Problem: prove that in two concentric circles, the chord of the larger circle that is also a tangent to the smaller circle is bisected at the point of contact. Solution: imagine two circles with the same center, O. Let AB be a chord of the larger circle that touches the smaller circle at point P. Since AB is tangent to the smaller circle at P, the radius OP is perpendicular to the chord AB. Now consider the larger circle. AB is a chord, and OP is a perpendicular line from the center to this chord. A fundamental property of circles is that a perpendicular from the center to a chord bisects the chord. Therefore, AP is equal to BP. Example 2. Angle relationship problem. Two tangents, TP and TQ, are drawn to a circle with center O from an external point T. Prove that the angle PTQ is equal to 2 times the angle OPQ. Solution: let the angle PTQ be represented by theta. Since TP and TQ are tangents from the same external point, the triangle TPQ is an isosceles triangle. This means the base angles TPQ and TQP are equal. Each is calculated as 1/2 of 180 degrees minus theta, which simplifies to 90 degrees minus 1/2 theta. We know from Theorem 10.1 that the angle OPT between the radius and the tangent is 90 degrees. The angle OPQ is the difference between angle OPT and angle TPQ. So angle OPQ equals 90 degrees minus 1/2 theta, which simplifies to 1/2 theta. Since theta is the angle PTQ, we have shown that angle OPQ is half of angle PTQ. Therefore, angle PTQ is equal to 2 times the angle OPQ. Example 3. Finding the length of a tangent problem. PQ is a chord of length 8 centimeters in a circle with a radius of 5 centimeters. The tangents at points P and Q intersect at an external point T. Find the length of the tangent TP. Solution. First, join the center O to the external point T. This line, OT, is the angle bisector of angle PTQ and is perpendicular to the chord PQ. Let's call the intersection point R. Since OT bisects the chord PQ, the length of PR is half of 8, which is 4 centimeters. Now consider the right-angled triangle OPR. Using the Pythagorean theorem, we can find the length of OR. OR is the square root of 5 squared minus 4 squared, which is the square root of 9, so OR is 3 centimeters. The right triangle TRP is similar to the right triangle PRO. Due to this similarity, the ratio of their sides is equal. This gives us the proportion. TP divided by PO equals RP divided by RO. Substituting the known values, TP divided by 5 equals 4 divided by 3. Solving for TP, we find that the length is 20 divided by 3 centimeters. Summary. In this chapter, you have learned the following key points about circles. The definition and meaning of a tangent to a circle. The tangent to a circle is perpendicular to the radius at the point of contact. The lengths of two tangents drawn from the same external point to a circle are equal. Thank you for learning with us.